that. Okay, hi everyone. Thanks for joining today. So today it's my pleasure to introduce Jiajun, who's just started as an assistant professor at Stanford University. And he's working on a lot of interesting things, applying program synthesis to computer vision to try to help understand the world. And in particular, I think you've done a lot of work on visual question answering and those kinds of topics. So yeah, I'll hand it over to you. So
Okay, it says host disabled screen sharing.
sorry, 1 second. Yeah, I'm gonna make you the co-host. Actually, I think
Okay.
that's okay.
Okay, yeah, I think now it works. Can people see my screen?
Yep. Yep.
Okay, great, thanks. So yeah, I'm very excited to be here, and thanks for the introduction, Oscar. Thanks for the invitation. I'm Jiajun Wu. I'm a new assistant professor started last July at Stanford. I got my PhD at MIT, so the year before. Working with Josh Tenenbaum and Bill Freeman. So I mostly focus on how to build scene understanding systems that take inspiration from human cognition. And one aspect of that, and is also what I'm going to talk about, also most relevant to this NSF expedition grant or the seminar series, is the visual world actually contains a lot of structures. As we can see, I show a few pictures above, right? There are a lot of structures like repetitions, regularities in objects, in shapes, in scenes. And how can we really exploit those for us to better understand the world? So yeah, the expedition is called Understanding the World Through Code. So I put the visual here because I'm going to focus on the vision part, computer vision part. Yeah, I also had some work, as Oscar said, connecting vision and language and understanding concepts, use that for question answering, capturing, or general knowledge representations. But I'm not going to actually talk about that in this talk. In this talk, it will be more like vision graphics, but with structure or programs as the guidance and how to integrate them with learning with deep neural networks. Okay, so let's start. Now we said there are a lot of structures in the visual world, right? So if you're walking in a corridor, MIT has that infinite corridor, right? You see that there's regularities, there are multiple planes, and there's also repetitions. Lights are repeating themselves, so you can imagine what will happen if you walk forward. You can imagine lights if you imagine how the scene will look like if you turn around. Then there should also be lights on the other side of the corridor, right? And of course, there are also like planes and structures and repetitions in buildings, in other scenes that you see in daily life. So these kind of structure often have several forms, right? One of them is, there are planes, regular planes, and there's symmetry. It could be reflectional symmetry, rotational symmetry. There's repetition. Repetition in terms of objects, in terms of windows and lights, but sometimes in terms of the elements in the scene. So you find that there's actually some correlation. It's interesting that this kind of structure is conceptually similar to the programs or code that we write for computer systems. So is that possible for us to integrate some kind of a program-like representations to use that to guide our understanding of the visual world for understanding scenes, but maybe also for downstream tasks such as image editing. So here is an example, right? Imagine we're seeing this building and we will wonder, how would the scene look like if the building becomes much taller? Right? Of course, we will expect the windows to repeat themselves, also following the 3D perspective projection structure. So we actually made a demo using our system, which I'll introduce later. We made a demo, but we use this Photoshop GUI, but it's not a function provided by Photoshop. We just use their GUI, and underlying that demo is actually our system's output. So what we can do is you can first use interactive segmentation. You can give it a bounding box, and then you'll be able to segment objects. And then the system will be able to smartly identify the vanishing point and finding the repeating structures in the scene so that you can easily edit the scene to make the building taller while following the 3D structure as well as following the repeating windows, right? The windows are really repeating themselves. So it does look very intuitive, at least to me. If you ask me how the building will look like if it's taller, I would say it should be something like that. So it turns out it is indeed possible to use these kind of structure for scene understanding, even for image editing. So let's see how this can be done. Our initial inspiration is actually from this paper. Kevin Ellis, Daniel Ricci, Armando, and Josh Tenenbaum back in Europe's 2018. So where they try to apply learning-based program synthesis for visual data. They first tried it on 2D hand drawings, right? If you observe some kind of drawings like this, and what they did in this paper is they first used learning and stochastic search to identify some primitives, right? Very basic elements of the scene or of the image. In terms of 2D line drawings, that means lines and rectangles. Right? And you can, of course, render them back to the original image. And then based on these primitives, they use learning-based program synthesis to synthesize a higher-level program, which includes, if or for these kind of program-like structure. And once you have this kind of programs, you should be able to easily, use that to extrapolate the scene. If I want to have 2 more rows or 2 more columns of the squares, then how would the image will look like? This is kind of a very interesting, and at least to me, I was like, okay, yeah, that does make a lot of sense. But it's only on 2D hand drawings. Can we extend that to 3D scenes? So our very first attempt is actually very similar to the 2D paper, but now we extend it to 3D. So you have to consider, perspective projections and things like that. You're going from a single image as well, but you identify, objects that belong to the same group. For every object, can you go from a single element to the groups that belongs to you? And then based on the groups, can you also synthesize programs to explain these scenes? And then you can, of course, use that for, things like scene extrapolation, right? If I have this kind of structure, how would the scene look like if I add another columns of the blocks, so that you can use that for image adding? Okay, this is our very first attempt, but this paper, although it's on 3D primitives and also the previous paper on 2D line drawings, it's cool, but it's very restricted, right? You have to assume that the world is only made of lines or rectangles, and in this example, the 3D example, the world is only made of spheres or cubes and cylinders. But the natural world is just much more complex than that. So of course we wonder, is there a chance that we can extend that to make it apply to natural images? Turned out we find a way. But before I introduce it, I was like, I'll share a story. That is, we feel like this is a kind of narrow area, not that many people are looking into it. So we're like, okay, if we want to imply programs, incorporate programs into, understanding natural images and editing natural images, we should have time. We can take our time. It's not like other AI topics that is very competitive. Turned out we are wrong, because while we were working on it, one day I look at arXiv, and I also found this paper from Oxford, which is really nice and share a very similar idea. So Oxford and Hattie Young and Maria Naik, they in ICML 2019, they actually also explored this idea. If I'm seeing images like this with multiple windows, and I want to ask you to extrapolate the image, right? Can I go from a partial image to the full image? Right? They're also able to synthesize a program with photo-like structures and to draw the corresponding patches so that you can complete the scene. It's not like perfect, but it's much better than purely learning-based baselines without considering these kind of program-like structures. Okay, I think what Oxford and co-authors did in this paper is they assume the whole scene is repeating themselves. So they assume the for loop is applied to the entire image. And then also on the other hand, they're learning or discovering these low-level patches using an autoencoder. Okay, so we took a slightly different approach because we want to think about, okay, what if the scene structure or the repeating structure is like in this image? You can see a number of serials. They clearly follow some structures, but it's not like occupying the entire image, right? So if we want to, apply this program-like structure only to part of the image, is there a more general way of detecting these repeating objects? So the key idea in this paper is we used a concept in computer vision called internal learning, or learning from a single image. It was originally proposed by Mihail Irani's group in 2011. So the key observations here is in an image, you can actually learn a lot from that single image, because elements in a single image are very likely to repeat themselves. The repetition can happen at the same scale. You can see that those kind of red squares. It can also appear at different scales. Objects, smaller objects or smaller patches may be very similar to a larger patch. This is because, perspective projection, the objects that are far away are smaller, but they could be essentially the same thing. Okay. So later, there's another paper which extended or exploited this idea, but combined that with deep learning. So for example, if you're given a picture like this, what they did is they compute activations of a deep neural networks that are trained to, for example, classify the image. For example, you can take AlexNet, right, appreciate AlexNet and apply it on this image, and then you can compute activations of the AlexNet for this image. And then you can take all these feature maps and compute, if you translate the feature maps a little bit, then what kind of offset will most likely lead to the highest correlation in the translated feature maps compared with the original feature maps, right? So what does this mean? This means if I move the image a little bit, or if I move the feature map a little bit, the outcome or the response is still most likely to be the same as before. This shows, okay, this kind of offset is most likely to be the gap between repeating objects, right? The distance between repeating objects, neighboring repeating objects in the image. And the benefit of using this kind of neural network activations instead of raw pixels is, in raw images, there could be a lot of noises due to, texture variations, due to the setup you have in data capturing, due to lighting variations, due to occlusions. But hopefully, AlexNet or any kind of neural network that are trained to understand images will be invariant to those variations, so that this kind of activations will lead to a more robust discovery of these repeating objects. So we adopted this idea. Of course, we made some minor changes, but we adopted this idea, taking activations and thinking about, what are the places, what are the offsets that really lead to the highest correlations. And this actually allows us to discover repeating objects from the images. And this is, you can think about this as a learned or latent or feature map-based primitives that is conceptually similar to the primitives that we showed before, like line drawings or rectangles for 2D scenes, 2D line drawings, and primitives as cubes for 3D scenes. But here, instead of assuming we know what the set of primitives could be, we turn into a learned approach or a feature-based approach that is more general and also doesn't have the restriction that objects has to be repeating throughout the entire image, right? It can be only part of the image. So now once you have that primitive, the story is the same. You can go in from that primitives and try to infer what are the programs that really explain the positions of these centroids of the objects. Now with that program representation, you can do something that you cannot do before, okay? So for example, if I'm now given an image like this with one repeating, with the repeating structure, but one missing region, and now I ask you to in-paint complete the image. So as humans, we have a very strong intuition that, of course, you can put some background and it will be a fine image locally. But as humans, we have a strong intuition saying, okay, there should be a cross there, right? So you can actually finding other crosses using the programs, and then send the patches of those crosses into another network just for image completion or image in-painting. So this is what we will get, right? With the guidance of the other similar objects discovered by the programs, you're able to, the network has learned to smartly blend these neighboring or reference patches to output another or the completed image with another cross. And the cross is not identical. If you look very carefully, it's not identical to any other crosses in the image, but the entire image just looks perfectly natural. Of course, you can use that for extrapolation, right? Similar applications as also in Osborne's paper as well. You can add another row of the crosses. Or the program also tells you, right, because I'm representing a centroid, so I know if the scene or the layout of these objects are regular or not regular, right? And I can say, okay, what if I want to make the scene a little bit more irregular, so I can magnify that deviation, and so that you can still, send edited position of these objects back into this neural network for smartly producing a natural image with the positions of these objects being moved a little, right, or more irregular. And going back to the serial example, it's the same story, right? You can use that program to help you to in-paint the serial. If that's one missing, then okay, I should put one there. Or to add another column of serial extrapolation, or to add it the scene regularity. Now we also tried on some other scenes with some repeating structure but natural images. And this is our completion results. This is like a zoomed in version of the missing region. Compare that with the ground truth, not identical, but I think it's pretty good. And here are a few other baselines where you can see that they have different levels of artifacts. Some of them look actually fine locally, but if you zoom out and look at the entire image, and you find that, okay, maybe you don't find locally, but they don't really respect the global program-like structure that the picture has. Okay, so this is like the main idea behind this paper, which we called Program-Guided Image Manipulators, published in ICCP 2019. And Jiajun and Xiuming Zhang are two co-first authors of the paper, and really did all the work. So they're both PhD students at MIT. Okay, so we now extended our model to natural images, but although we don't assume objects are repeating throughout the entire image, we still make assumption that is objects all lie on the same plane. And also the plane we're looking from it, from I would say a top-down manner, right? So there's no perspective distortion. But what if the picture is like this, right? This is, maybe more common, more general, right? Because, you're not taking the picture from up front, but there is a perspective distortion. And so the position of the objects are not that regular anymore. So is there a way that we can incorporate camera poses to better model the scene so that your program of the scene should not only have this kind of for loop-like structure with learned, entry-level primitives, but also have a camera pose parameter. So if you can really use that camera pose parameter, you should be able to now rectify the image, right? So to undo the perspective projection, so that your program will be, easy to explain the regular structure or repeating objects in the image. So this is like a natural extension of our previous work, because now we want to no longer assume we're looking at a scene from a certain top-down, camera position or viewpoint. Okay. The key observation in this work is we found that camera pose estimation and visual program synthesis can really help each other. And actually solving each of them without considering the other is very challenging. Okay, so for example, in this input image, if I just wanted to say have a deep neural network or any learning system that directly estimate the camera pose of this image, then it turned out to be really hard. You can try to estimate the camera pose. We use the state-of-the-art method called PlayNet, and then we use that to estimate the camera pose and then to rectify the image. It's not really that good, right? Still, there is some distortion happening. Or if you don't consider the camera pose, just directly run our previous methods, it completely fails. Because the objects are in a very different scales, and also they're not that regular. If you look at the positions, the centroids, right, of these objects, they're not really that regular. So what's new in this paper as a follow-up in CVPR 2020 is we propose to do joint inference. We have this image, and we want to solve two problems at the same time. The first problem is program-based camera pose estimation. Once we have that program, can we use that to guide our inference of the camera pose? And the other is what we call a perspective-aware program synthesis. So we want to do program synthesis. We want to take perspectives. We want to take camera pose into account. So we want to rectify the image before we try to synthesize the program on top of that. Right, so we actually turned out to be doing an iterative inference algorithm. So you can see that first, we try to estimate a pose, and then we use that to estimate a program. And then we try to think about, what are the poses that really help you to get you the best program that best explain the input image, right? Because if your camera pose is really wrong, then your estimated program couldn't be very good, right? Because the centroids of these objects are not irregular, and there's no way a program can explain them well, right? And so these should really help each other, and we do iterative inference of camera pose and the programs, and eventually, our system is able to really rectify the image to get you the correct camera pose, including the pitch and yaw, as well as inferring the right programs. Right. You can see that after we get the correct camera pose, after you rectify the image, then the positions, right, or the centroids of these objects are much more regular, right? And your program can explain the positions of these centroids much better. So we're solving two tasks, so we want to evaluate on these two tasks. And first is camera pose estimation. We compare with a number of baselines, and including state-of-the-art based on deep learning. And apparently our algorithm just works much better in terms of inferring camera pose estimation. We also tried on the other tasks, right, how the program can really help us. In the case of, for example, imaging painting, and by taking camera pose into account and do program synthesis on the rectified image in painting, and then you can again, do perspective projection to turn the image into the original camera pose. And you're able to do better to synthesize the image while following the regularity structure in the picture.
Could I just ask a quick clarifying question?
Yeah, sure, of course.
What do you have some intuition behind what the reason was that the camera pose failed when you didn't incorporate program structure? Was there some?
Oh, it's not like, oh, okay, so let me clarify. Maybe I'm saying two things at a time. So the first is camera pose estimation. The first message I want to say is the camera pose estimation itself is actually really hard. So if we just directly do it, you take a pre-trained model, then the pre-trained model usually train on what? On indoor scenes and those kind of data. So if you train on those kind of data in natural images, but you test it on these kind of, it's still, I would say it's a natural image, but maybe not the most common natural image that you will see in your life, then it often fails. And why what I'm trying to say here, the second message is, although it fails, program can actually help you, because only if you think about it, if you try out different, I would say, I don't know what the exact camera pose is, and maybe I have a few candidates. And for each of them, I can try to think about what the right program is. And turns out only the correct camera pose will lead to the best will lead to a rectified image which the program can best explain, right? Because if the camera pose is really wrong, then there's no way you can synthesize a good program that really explains the objects in the image. Does that make sense?
Yeah, got it. Thanks.
Thank you. Okay, so yeah, this is better. We now can deal with objects on a single plane, and the plane can have, there could be a camera pose variation, right? But natural images, often there are like multiple planes, right? If you look at this corridor picture I showed before, okay, that's nice, but it has, at least 4 planes, right? So can we actually try to generalize it in multiple planes? Turns out this is also even possible. As another follow-up to our previous work, we try to extend it to not a single plane, but multiple planes. So now you're really going to the space of, I would say, not fully 3D, because you actually make assumption that the objects are made of multiple planes. So I would say it's maybe more like 2.5D, where you try to set camera pose, and then you want to identify how can I partition the scene or the image into multiple planes. And then every plane, as we said before, it can have the positions and the normals, right? These are like camera parameters. And you can synthesize the programs for each plane separately. And this is a much harder problem. And so again, we want to leverage some low-level cues, visual cues. So the cues we leverage are now in like 3D or 2.5D, including what's the vanishing point of the image. We first use a pre-trained vanishing point estimation network to estimate the vanishing point of the image. And then we can also use the detected wireframe to guide our partition of the scene, right? The difficulty or the new things here is we'll have to partition the scene into multiple planes. But how can we do that? Although this may look very different from what we did before, turn out conceptually, again, it's very similar in the sense that, to synthesize program for line joins, we first find primitives. Those primitives are lines and rectangles or squares. To synthesize programs for single plane images, we want to find low-level cues, and low-level cues there are repeated activations, or which hopefully correspond to repeated objects. And here you want to synthesize planes for I think I accidentally called Siri. So can people still hear me? Because there's some.
Yeah, I can hear this.
Okay, good. Because my machine suddenly says like Siri or something. Sorry about that. Okay. Yeah. So for the case of multiple planes images, so what's the bottom-up visual cues here? The cues here are the vanishing point and wireframes, and we want to think about how these low-level cues like vanishing point and wireframe, just like lines and shapes or primitive shapes, can help us to partition the scene and let us to synthesize high-level programs. And here the idea is actually similar to the thing I just talked about in a single plane setup. That is, we wonder if these bottom-up visual cues and high-level programs may help each other. Again, so vanishing point and wireframes are nice, but the wireframe segmentation is a really hard problem. And you can see that the detected wireframes, right, from any pre-trained models is just extremely dense, and there are a lot of like noises or uncertainties. You have multiple candidates, many candidates that you can use to partition the scene, right? If I'm giving a corridor picture like this, I can say, okay, it's pretty clear that it has 4 planes, but based on the wireframe and based on the vanishing point, there are just many ways that I can partition the 4 planes. right? Partition the image into 4 planes. But which one is actually correct? Right? So just like camera poles and program synthesis can help each other, we found out that plane partition and program synthesis can help each other too. So what we did is you can take each candidate of plane partition, back project it into 3D, so that you can really expand the plane and do an perspective projection so that you get the 4 planes. And then for each of a plane, you can actually also try to synthesize the program, right? What is the best program that can explain the observations or explain that plane after I have n perspective? I have to do a perspective projection, but in the other direction to unwrap it so that you have this 2D image of that plane. You can see that if my partition is really wrong or very off, then elements or visual pixels, right, from 2 different planes will be merged into 1 plane. And after you back project it and unwrap it, it will lead to some really weird structure that's very hard to be explained by a program. And on the other hand, if your partition is correct, then after unwrap it, you will see very clear and repeating structures like the lights, right? And these things are much better explained by a program. So you can actually use, again, how the program explain your visual data to guide your partition of the scene. So here, plane partition and program synthesis, again, help each other. And it helps us to identify the right candidate. Okay, the second one is really the best. Once you have been able to partition the plane and to identify the repeating structures in that plane, then now you can really do visual synthesis. Imagine how the scene will look like if you walk forward. Right. We compare with another pure pixel-based scene synthesis methods. It actually really works very well on general scenes. But if we ask them to do something that's really challenging, for example, keep going forward, right? Keep going forward, then these recurrent-based methods will turn to be very blurry. But with the guidance of the program, then we have the intuition that okay, the lights should be repeating themselves, and if I want to look to the top left, then there should be another light coming in, right? Because the program is telling me lights are repeating themselves, so I should have another light coming in. But if you compare with the baseline, it can only give you something that's kind of smooth but also blurry.
Quickly, Zena had a question. Are you learning both the program structure and the real valued parameters here?
What is the real value parameters? What do
I
you
mean,
mean by
I guess the parameters in the program, is it just the parameters in the program, or are you also learning the structure of the program?
Oh, we're also learning the structure of the program.
Okay, and can you, just out of curiosity, can you say a little bit about how you, what kind of an algorithm you use to do that?
Yeah, we have a pretty strong restriction on what kind of programs it could be. So we only consider, we actually only consider things like the for loop structures, and then there's no if or branching statements. So we only consider the objects that can be repeating themselves, and the for loops can have circular structures or the rectangular, so you can have 2-dimensional for loops, and these are the candidates we consider. And then I think what we did for the structure there is we just search a number of candidates, and then we try to use that to explain to fit the input view, the visual data of that plane after you unwrap it, and see which one is the best. Yeah. So the synthesis, the structure part is really search based. It's not learned. Yeah.
Got it. Thanks.
Yeah, and then you can do working backward, right? So how would it look like if you work a little bit backward? Again, lights should come in, and you can imagine how the scene will look like if you like to turn around, right? You can see, I got inspiration from MIT, this infinite corridor. So okay, we can actually reproduce that infinite corridor. Of course, in practice, no corridor is infinite. But this is something that I guess one plausible explanation, given the limited observation you have, right? You can compare with the baseline. It's really hard for them to synthesize things that they've never seen before. And you can use that for extrapolation. Right? This is like the demo I showed at the beginning. If you want to make the building taller, now you can have multiple planes. You estimate their camera poles and viewpoint and orientations, and then you can use the program to guide your synthesis of these planes. So this is joint work with the 2 main authors, leading authors, Jiajun again and Yikai Li. Jiajun is PhD student at MIT with Josh and Leslie Kelvin, and Yikai was a visiting student with us for a year. Okay, so a quick summary is we going from visual program synthesis, uh, line joins and primitives, and then we go to single image learning with general objects, and then we simultaneously estimate the camera parameters so you can work with a single plane but with perspective distortion, and then you're going from single plane to multiple planes that you can do view synthesis or scene editing with objects that have 3D structure. So what's next? So I want to give a few very brief discussion about the recent work that we have done. I don't think I'll have time to talk about them in very detail, but I try to give a high-level picture about what we have done and how they are connected to the existing work that we have tried before, and hope to we will be able to have more discussions after that. So what's next? Now, if you think about this kind of this line of work, then essentially we're going from 2D, estimating 2D objects and their positions, or objects in a single plane, to I would say in some sense 2.1D, because you're not assuming you're looking at the scene from top down, but there could be a camera parameter. Essentially, to I would say not really 3D, but 2.5D, because you're assuming the scene has made of multiple planes, and every plane may have their orientation, but it's not really like full geometry. Right? So you're going from 2.5D to 2.1D to 2.5D. So very naturally, we wonder, right, is that possible for us to do 3D shape explanation using programs? Because shapes, essentially man-made objects, right, they often have this kind of abstract and program-like structure. So can we actually use programs to explain 3D shapes? There has been a lot of work in this direction, right? Especially in computer graphics. There's like L systems, which you can explain a hierarchical 3D structure using very simple equations. And there's like probabilistic context-free grammar or work that use symmetry to model 3D shapes. And of course, there is also the inverse CSG paper also from Wojciech's group and Armando's group, how you may explain a 3D structure by invert the CSG, so they can actually infer the CSG program that explain that scene or the shape. And recently, and this is the data set I mentioned, they have this Fusion 360 data set where you can see there are a lot of CAD models where they also have sketches about how these CAD models are actually made. It's kind of very interesting, exciting direction, and apparently a lot of people are looking into it. But all this work, from computer graphics, also including inverse CSG, is purely inference based. So there's not really learning going on. I'm given a shape, so I don't have to learn anything. But also I can work on any shapes I'm given. Okay, if you give me a shape, I just do an inference algorithm, and I can try to infer what are the programs that really explain, the CSG that explain the shape. So we wonder if it's possible to use learning to actually, make the inference at least much faster. For example, that's kind of one benefit of having a learning-based system, right? So we made a first attempt. We designed things we call this shape domain specific language, or shape DSL, which is something we believe what man-made objects, especially furnitures, are often look like. And then we designed a neural network-based program generator and a neural network-based program executor, try to translate from a 3D shape to the underlying shape program. Due to time constraint, I think I have like maybe another 15 minutes. So I don't have time to actually talk about this in detail, but I'm really happy to talk offline, because I think this is kind of a very exciting direction, but also on the other hand, kind of underexplored. And also our approach also have a lot of limitations, because for example, we assume the n-level primitives always have to be like cylinders or cubes. But anyway, we built a learning-based system that are able to translate the 3D shapes into underlying shape programs. And what's the benefit of this kind of shape program representation? Now, it actually has a lot of applications. For example, in single image 3D shape reconstruction, if you're given an image and you want to reconstruct the shape, then this is what people can get often, which is something that you can see that, okay, the reconstructed 3D shape look, it's not too bad. But if you look at from the top, right, you find that the tabletop has this weird shape that doesn't match our intuition, because humans have such strong intuition that the top of the table should be like round given this input image. But this is not something that we can easily solve if you just do everything from a single image without this kind of priors. Because if you look at the reconstructions from the input viewpoint, then you find that from the input viewpoint, the reconstruction already looks very similar to the input image. And so there's not that much signals you can get from the input image. Instead, you have to resort to a priors of shape had this program-like structure. So if you reconstruct it into this shape program representation using our program generator to translate that, and this is what you're going to get. The top now looks much better and matches our intuition better. Yeah. Again, I will talk about the details of this paper offline due to time constraint. This is joint work with Yonglong Tian, another PhD student co-advised by Josh and Philip Isola. Okay. So after we're done with this work, so sometimes we wonder, right? Why would this program structure exist in the first place? Our impression is the visual world is kind of messy and there are a lot of arbitrary structures and unorganized. But why would these programless structure exist in the first place? I think it's because these man-made objects are made by humans, right? They're man-made, so made by humans. So when humans are making these objects, they put in their own priors into the manufacturing process. So it's actually because of the priors that humans made when they're making these objects. So then we wonder, okay, if these things exist, these program structure exist, then it really exists in terms of an object shape, right? Object shape is the thing that really has a kind of regular structure. But there are also other things. If you take a natural picture, then you're seeing the object, you're seeing its shape, but you're also seeing it in the particular lighting conditions. There are reflections, there could be noises. These things doesn't have that kind of regular structure, right? Only the shape or maybe a little bit of texture may have that regular structure. So is that something that we can exploit, right? Can we exploit the fact that only shapes or maybe some textures have that regular structure, but not lighting, to help us to better understand the object? So this goes to our later work, which we called single image de-rendering. So if I'm giving you a picture of a vase like this, the vase has a lot of, if you want to really understand it, right, you can say, okay, the picture can actually be decomposed into many what people call intrinsic images, right? So it includes the object surface normals, which is essentially the shape of the object in 3D. It includes the albedo, you can see it's like the texture or the color of the object. It also includes object material. There is a diffuse reflection, there is specular. We can see that there are regions of the pictures that are much lighter than others because there is the specularity, right? And there's the environment map. That is, this is for what's the lighting of the environment surrounding the object. Okay, so if you just look at a pixel, if you look at RGB values, of course, these bright regions are going to be very different than those dark regions, right? But we have a strong prior that because humans made this vase, and there should be some program-like regular structure in terms of the surface normals, right? In terms of the geometry of the object. And also it should have some priors on albedo, right? Albedo may not be identical, it's not a uniform color object, but you feel like, right, had a strong impression that, okay, these kind of different patches, they're more or less alike, alike in the sense of, how you feel about it, right? And the specular regions or these kind of, lighting conditions are not that regular. So can we actually use that asymmetry, right? The objects on the top, normals or light, or normals or albedos are more regular, and specular or those lighting conditions are not that regular, to help us to disentangle and decompose that image into these intrinsic images. This is kind of very hard problem in computer vision. It's a fundamentally challenging problem because it's very ambiguous, right? You can imagine the scene, I can even imagine it's like a painting in 2D, right? So there's no 3D structure at all. Or it can be an actual vase in the lighting condition. I guess many of you have seen all those visual illusions, right? Something looks 3D, turn out to be 2D, something looks concave, turn out to be convex, right? So this is fundamentally ambiguous problem, very hard in computer vision, especially if you want to do it from a single image. But now we wonder if we can use this asymmetry or use the program-like structure that exists, the priors that we have in object shape to help us to solve this problem. And once you can decompose the image, what you can do is now you can synthesize the objects in different view. Right. Just all from a single image, or you can relight it. So this is joint work with Ilya Wu, who is a PhD student from Oxford, and while he was an intern at Google. I spent a year at Google before I started at Stanford. So this is some joint effort there. Okay. So the training pipeline, or our model, is actually very simple. First, we focus on objects that have a certain program-like structure. Here, we restrict ourselves to only look into objects with a solid resolution structure. Okay, so which means the object shape, we assume it can be represented as a solid of a resolution structure. So like things like a vase. And once you make that assumption, in some sense, you can say the SOR representation is a very weak form of programs. Right? Once you have that assumption about object shape in terms of programs, then you can use that program to unwrap the object. You can get a surface novels, you can get a texture maps, and you can use neural networks to going from the unwrapped texture maps to actually and the surface normals to estimate environment lighting and the material, and also to estimate object color or albedo. You can then use that to reconstruct the original image. So this is like the de-rendering process. On the right, this is like the rendering process, right? Once you have the lighting, once you have the color, once you have the object shape, you can re-render the original picture. And of course, there could be a reconstruction loss, right? You want the reconstruction of the base to be similar to the input. Okay, this is like the first loss term. And then now we want to use our priors. Our priors are like, okay, SOR shapes can help us to reconstruct image, but also, because the vase is made by humans and it should have like uniform texture. So we compute a mean albedo, and then we again combine that with the shape and lighting. So that we want to re-render or regenerate another vase, but with the albedo as its mean. And again, we want it to be similar to the input image. Okay, this is like the second term.
Wait, sorry, I'm a little, I guess there's a lot going on here. So which parts of these are learned roughly, and which parts are like kind of some handcraft?
Only the three Fs on the left is learned. Actually, the shape is actually even pre-trained. So so basically, you're essentially learning to decompose the image. Once you can easily estimate, right, what's the SOR representations or for the shape of the object, then you can use that to unwrap the scene. And now what you have to learn is these two networks, one for estimating lighting and the other for estimating albedo or the color. Yeah, after that, everything else is, you can write down, these are, like equations in the graphics unit. You can write it down and then we implement it in a PyTorch or something. Actually in TensorFlow, because this is a Google for that. Yeah. And you can reconstruct the image. So everything that is being learned is the three neural networks on the left.
Got it. So the normal map and the texture map just come from the shape.
The normal map, yeah, comes from the image, right? Because once you have the SOR, it's like the shape representation. You have the normal. And then once you have the normal, you're able to unwrap, right? You can unwrap the pixels, resample from it, then you will get a texture map.
Okay, got it.
Yeah. Okay, but this is actually not enough. There's one more, Oscar, there's one more component that is need to be learned. And I think this is like most important. Because albedo, you say, okay, objects, we feel like if we made that vase, then the object itself should have similar textures, right, everywhere. So what does it mean by similar? Okay, one thing you can say is, okay, I can just blur it. I can compute a mean, and the reconstructed image using the mean should also be similar to the original image. But another thing that we observe is you can actually, if you directly compare pixel values, that doesn't work, right? Because the textures can be very different, right? There could be like complex patterns, and some can be much brighter, some can be much darker. So just compare pixel values doesn't work. So one way is to use the mean. And the other is we try to actually use a learned feature maps or learned metrics, right? Can we use a learned like a discriminator as in GANs to say, if I sample different patches from the albedo or from the texture map, then the different patches should still look alike. So this is very important. This is like the key innovation, I think, in this work, is what we call a self-supervised albedo discriminator. Again, we use the prior that once you have the program-like representation for shapes, you can unwrap it. And once you have the priors that the object is made of same material or similar textures, you can exploit a similar texture in the form of this self-supervised albedo discriminator. So for example, if you can predict, these are predicted albedo map. And what is most likely going wrong is, when there is specularity. If there is specularity, then often the region looks very, very bright and it's like white even. In that case, it's hard to get albedo right. So, but we do have this strong prior that, the specularity is irregular. It's some noise, from the lighting conditions, but the object itself should be regular. So, turn out what we did is we randomly sample patches sorted by variance of specularity. I have some patches from regions with low specularity. I also have some patches from regions with very high specularity. And I have a discriminator which try to classify whether that patches are actually from a similar. I have a discriminator that try to classify if a pair of patches are from regions with similar specularity, they're both very dark, or they're from regions of very different specularity. One is very bright or one is very dark. our goal here is to say, the intuition here is to say, the object should have similar textures. No matter what the specularity is, the albedo should really look alike, right? So the generated albedo should be able to confuse the discriminator, and discriminator should not be able to classify whether an albedo patch is from a region with high specularity or from a low specularity. Okay, with that discriminator, this is really the key for our performance for the system to work. Then we're able to, given from a single image, to decompose it into surface normals, albedos, diffuse specularities, and material maps and environment maps. And we can use that for turning a single image into 3D and for novel view synthesis. These are all like from a single image during testing. As well as for relighting. So these are from the training set. We trained it on the data set of vases from the Metropolitan Museum, but we also tested images outside the data set. Okay. So here are some images we take from another data set. These are like vases in the wild. Our system still works pretty well on decomposing into normals, albedos, diffuse maps, specularities, and materials. And again, for these, in the wild bases, you're also able to, going from a single image to get its 3D shape, including there's like even some paintings, as you can see here. You're able to get a shape of that base, synthesize novel views, and relight it. Okay, so these are some attempts in extending the use of programs to use that to explain 3D shapes, but also in turn to think about how this kind of program-like structure can help us to not explain 3D shapes themselves, but to help us to understand the 3D structure in images so that we can decompose the image into intrinsic images and support other tasks, looking around or relighting. So this is going from 2D to 10.5D to 3D. What is the other dimension that we never talked about? That is time, right? So if you look at this human doing exercise, jumping jacks or squats, these kind of exercise equations, then you find there's strong regularity structure that exists in the human's motion over time. So this is the motivation of the final piece of work that I'm going to present. That is how we can use program structure to explain human motion over time. So if I decompose the motion into different frames, and I can estimate or infer the poses of these the humans over time, and you can see that there's kind of very strong regularity in the motion, actually also in the trajectories of the key points. This is the case for jumping jacks. This is also the case for the squat example. Right? I decompose into different frames. I do a pose estimation. Again, there's kind of a very strong regularity. I can easily decompose the sequence into, say, okay, at first the person is moving hands up, and later she's moving hands down, right? It's kind of a symmetric structure. And in the squat example, the person is first squatting down and then standing up. And then, there could be a case where the person is not really doing much and taking a break. So together with Alex Icahn, but the leading author is really Sumis Kulao, who is a co-advised student by me and Alex. We try to think about if there's a way that we can synthesize what we call motion programs to explain human motions so that we can better understand these exercise videos and use it to do things, other applications as we'll show. Again, I guess conceptually, all these papers, they have this similar idea, that is, what are the low-level visual cues we can exploit? And going from those low-level visual cues, right, how can we synthesize high-level programs? So we discover, first, the system also has two steps, therefore. The first step is to synthesize single primitives. Going from circular motion, like an input video, you can actually detect the key points, and you can regress or fit a circular motion primitive. And we also consider linear motion primitives. You can detect the key points, and you can explain the motion of the key points using linear motion primitives. So you can do that for the entire video, and you can explain the video, the trajectories of the key point for the entire video, in the form of a number of what we call concrete motion programs, right? There are a number of primitives. And then you go from there, you try to discover what we call as abstract motion programs. Again, thinking about searching for the for loops that can really best compress the program and to explain human motion in a condensed way. The concrete primitives can, the abstract programs, motion programs can later, it actually models, what's the distribution of the duration or of the starting and middle and ending point of actually concrete programs, so that you can actually sample concrete programs from the abstract motion programs if you want to synthesize future motions. So the benefit of representing scenes or representing motions as with this program-like structure is it allows you to do things that require some reasoning and you can't really do from local, smart, just local blending of patches as you can do with GANs. So for example, there's a task called video interpolation, right? If I have a video, I only observe very sparse samples of the video. I want to synthesize the human motion from it. If my observation is pretty dense, then I can easily use a GAN, whatever, to blend things together and to synthesize the smooth motion. But if my observation is very sparse, then this is what we get with like a GAN-based framework. I only observe actually 3 frames: the starting frame, the middle frame, and the final frame. And if I want to do this kind of interpolation 8 times in this input video, then a purely GAN-based framework will have very strong artifacts. It looks like the hand is just disappearing from one place and reappearing from the other place. But if I'm explaining the motion with the program and use that to guide the synthesis of future motions, or sorry, to guide the synthesis of the motions in between, then you can see a more smooth interpolated video of the human motion. We're not really modeling the pole, so it's really just we're not modeling the cup, but we're just really modeling the human motion itself. You can see that synthesized motion is much more smooth. And there is some quantitative evaluation about how our method compare with the baselines without using motion programs, and we do better in both in terms of the key point estimation error as well as the perceptual metrics. And we also ask humans which one look better or look more intuitive to them. And it turns out that our model is basically comparable with the baselines if we were just doing interpolation at 2 times, right? So if I'm sampling every other frame and ask the system to do interpolation, then there's not that many benefits from the motion programs. And all these methods, the humans say, oh, they're probably equally good. But if you look into a much more challenging case where you want to do 8 times video interpolation, where the observations is really sparse, then your system can do, our results are much strongly favored. Another task we're looking into is video prediction, right? Going from part of the observation to predict what's going to happen in the future. And if you look at this human running, then these are like the future frames that you will expect to see. If I'm seeing only part of the running process, then ask the humans to predict what's going to happen in the future. Then we can compare with, again, just purely pixel-based deep learning systems. In the first 300 frames, they're equally good. Our systems with the guidance of motion programs is really just equally good if you compare that with the baselines. They all look pretty natural. But if you want to solve a much more challenging problem, if you want to do very long-term video synthesis, in 600 and 900 frames, I just keep asking the system to synthesize what's going to happen in the future. Then you can see that the learning-based method becomes very unnatural, and there are a lot of artifacts because of the accumulation of errors. Right? If you compare that with our method still can do very reasonable synthesis, even in the very long term after 900 frames, like 30 seconds, while the baseline is just not doing anything. That's kind of, you can see that pretty strong artifacts. So similarly, we did a comparison in terms of quantitative numbers. You can see that in the long term, if you go especially over time to synthesize many frames, then our results are much better with lower errors. And also similarly in terms of human study, again, in the first 300 frames, they're like equally good. But if you ask the results ask about the results in 600 to 900 frames, then our results are much more favored because we have the program that really tells us, okay, what these motions should be like, even in the long term, in terms of the prediction task. Okay, so this is like a summary of the work I presented, going from how the program or this kind of structure can help us to understand visual world from 2D to 2.5D to 3D, and also now to understanding temporal motion. So the key idea here, obviously understanding visual world through code. The key idea here is we want to use neural networks for things that neural networks are really good at, right? As I said at the very beginning, what is an object? What is a serial? That seems really hard to explain using programs. So why don't we just ask neural networks to learn these low-level primitives for us, right? And what is how to represent a right texture map, how to represent a right albedo? And that seems really hard. Why don't we just ask neural networks to learn it for us? But on the other hand, programs, especially those kind of man-made priors, right? Objects are regular when we made them, when we manufacture them, they're made to be regular. And these kind of regular structures in objects, in scenes, the repetitions, the symmetry, really help us to do better generalization. We can see much better generalization results, even to cases, extrapolation results to cases that we never seen during training. This is something that neural networks are not very good at. So also the key innovations behind all these works is we always say we use neural networks to find some low-level visual cues, and then we use programs to help us to generalize and combine them with neural networks for even very downstream computer vision tasks like video synthesis, shape synthesis, relighting, and stuff like that. So what's next? Of course, we're interested in working on more general scenes, right? There are scenes like this. I took a screenshot from the movie Inception, right? Of course, there are regular structures. The columns are repeating themselves, but also there are a lot of things that are not kind of program-like. There were things like the skies and even like the tree structures. These things are maybe hard to model using programs. So maybe when you think about how to blend those kind of program-guided scene representation with more like latent feature-based scene representation. We're also interested in methodology because one problem we encounter, actually Zena was asking, right? So what's the role of symbols in programs? What should be really represented as programs? What should be represented as learned methods? And how can we really do good inference? Right? Because we have to resort to search because it's so hard to synthesize the right program. In many cases, we have to resort to search. So if we can come up with more efficient inference algorithms, that would be great. And more generally, we want to go beyond from perception to maybe even action. Right? So we have talking about, what does it mean by standing up? I can represent the motion, represent the key point as programs. But is that possible to use a program-like structure to explain more high-level concepts? As Oscar said, I have another line of work, understanding or representing concepts from language for question answering. But if we can represent, what does it mean by, for example, I'm throwing water? What does it mean by in a soccer game, I'm trying to pass the ball to my teammate? There are actually a lot of like program-like structure or logical structure there. So actually together with Josh and also Leslie Calvin from MIT and some psychologists at Harvard, we're trying to explore, is that possible to integrate these kind of neurosymbolic representations for explaining actions? Especially even if we look further into multi-agent setting, right? Can you actually explain the coordinations and cooperations across multiple agents? And that's kind of a very exciting direction in the future. And as well as, of course, its connection to language. So going from vision to really understanding the scene to cognition with the help of language. There's also some ongoing collaboration that we have with Noah Goodman at Stanford, which I think is also part of this expedition team, about extending this kind of work by connecting concepts or connecting them to words. Okay, so that's the end of my talk. I think, sorry, it's a little too long, but really I appreciate the great work from all my collaborators, students, and colleagues. And thank you for listening. Any questions?
Yeah, thanks so much for the great talk, Jiajun. So I think we are a bit over time, but we can take a few questions if people have any.
I have a question. If that's okay.
Yeah, Zena, go ahead. Yeah.
Yeah. So in the vase example, it's really neat that you. So it seems like you kind of separated neatly the programmatic structure and all the learned lower level structure, right? And that's a really good example to do that. But it seems like in the real world, it's hard to see where this boundary lies. So for example, if I have a vase and then suddenly I break it, right? So it no longer has this nice kind of symmetry. Is there a point where I decide that it's no longer programmatic and I need a different representation, or do you imagine some other kind of representation which could both handle a normal vase and also a broken vase at the same time?
That's a very good point. I think even if it's broken, let's see. I think the motivation here is, you have the space and then it has this circular structure. So using that, the solid revolution is really to use that to guide us to say, okay, what are the surface, and then these surfaces should share the same texture, right? At least in the perceptual sense, that they should share the same texture. So in the case of a broken vase, maybe easier, because now if the pieces are really small and mostly flat, then you no longer need that kind of solid SOR representation. As long as you can group or the scene or the input into these different pieces, and then every piece of the broken vase, okay, I'll say now this is a piece of the vase, it's broken, but that's a piece. And then because it's part of an object, it should have a similar texture. So maybe you no longer need that program structure. Does that make sense?
Yeah, but then I guess there's also, maybe that's too extreme. It seems like a lot of real world objects have, maybe not a broken vase, but like a dented vase, right? Or like some imperfections.
Yeah, that's true. So for that, I have another comment. So the work we're doing here is, we made the assumption that the object is rotationally symmetric, right? So this is actually based on earlier work of that paper. So there's let me try to find the slide. So the first author of this paper, Ilya Wu, is really great person and very talented. And our work here is actually based on his earlier work, where he tried to exploit an even weaker form of program that is reflectional symmetry. So he said, if you take a single picture of a human face or a cat face, right, it's most likely to be symmetric, right? So is that possible for us to explore that kind of symmetry and use that to infer, doing basically essentially the same thing, inferring the human face and stuff? And that paper, I know, they submitted a paper twice. The first time it got rejected, and the second time it was selected as CVPR best paper. So there's a huge difference. What made that huge difference is they added something called a confidence map. So it's actually responding to the concern you had. That is, human faces are mostly symmetric, but there are cases where it's not fully symmetric. There may be, some kind of the hairs or stuff like that, right? They're just not completely symmetric. So they're saying I have another confidence map. I can, if it's symmetric, means if I flip the object, then it should look identical. But if there's an additional confidence map, then I should only consider places where I'm mostly confident that it should be symmetric. So engineering-wise, there's a trick that they exploited and to really improve the performance. But conceptually, right, what's the right general representation to combine, regular things like programs like structure to irregular things. The irregularities can be small, like a dented vase, can be large, like a broken vase. I think this is like the fundamental question that everyone is asking. Some people say we just discard the programs at all, right? Just they're deep networks and they can smartly approximate anything. And Oscar and Armando probably don't agree. So I think we're just trying to find the middle ground that really get the best of both worlds.
Cool, thank you.
Any other questions? So I had one question. So you really emphasized kind of the single image in this project, the slide right now. Like you really emphasize the single image. But when humans are looking at objects, they don't have a single image. They have you're seeing it from different perspectives, and you have like a video kind of view of the object. So have you thought about how these techniques might work in cases where you can kind of actively explore the object from different views? Does that make the problem easier possibly, or?
I think the reason that we're looking into single image is mostly because, if you have multiple views of the object, especially if you know the viewpoint, it sounds like if you want to do expert exploration, then you can actually see an object from different viewpoint. If you can have multiple views of the object and also you know the viewpoint, then the problem is not that hard in computer vision because people can use techniques they call multi-view stereo to actually easily reconstruct the shape. And then they can use that to, and especially if you see it from multiple views, then the specularities will move. So then it's no longer a hard problem to disentangle these kind of, to distill the intrinsic images from the input. So this is, I guess we're putting in this setting because that's kind of a meaningful problem to study in computer vision. And also, although I agree with you in the sense that, humans, we see an object, at least first we have two eyes, so it's not single view, it's stereo, and then we can work around or stuff like that. But on the other hand, if you're just giving me this image, right? Now thinking about it, I'm not doing training, I'm doing testing. If you're testing me, you just give me a single image like this, and you only allow me to see it with one eye. I should still be able to, have a rough understanding of the geometry and normals and albedo of the object. Right? So in practice, we don't do that, but it doesn't mean we don't have the ability to do that. So in that sense, we want to replicate the abilities in machines.
Yeah, I guess I'm thinking of it like at training time, like you could imagine using videos to get like.
Oh, there are a lot of works on that actually. During training time, I can have videos and more supervision. During testing, I just have a single view. But you have already something learned the ability to infer from a single image. Yeah, that's true. We didn't do that from a practical reason. That is, we don't have that kind of data. We work on vases, and we use the data set from the Met Museum, and they took a lot of nice pictures of the vases, but it's all from a single view. So we just don't have that data. But it's kind of a general case in computer vision as well. It's much easier to get single image data. You can do Google image search compared with either active learning, the multi-view data, or even active viewpoint data. That's kind of very hard. Okay. So.
Right. Okay. Thanks. I guess, yeah, we might have time for just one more question if there's anyone. Otherwise, yeah, we're a bit over time. So. Okay. Yeah, thanks so much, Jiajun, for the talk. And
yeah, thanks. Nice to see everyone. Thanks for inviting me.
So, yeah, I'll see all of you next time, next month. Bye.